Don, let us hear some more about testing and carbon and in dollars. The floor is yours.
Thank you very much. And making sure I have control of the screen here. Yeah, I do. Okay. So I'm going to pivot us a little bit here. And so just quickly myself, Don Davies, I'm the president of Magnusson, Klemencic Associates. We're a 200-person structural and civil engineering firm. We're in Seattle, but we work across the country and the globe. And I'm mostly going to talk about some Midwest projects here. But more than anything, I want to reframe the conversation here and focus on two key topics. Frankly, how our clients today are looking at what I'm going to call double bottom line decision making, looking at cost and carbon footprint together. And I want to try to help describe for you how we can start bringing embodied carbon into how we talk and show value to our clients of what we're doing. And I'm going to take you, I'm also going to walk you through a series of case studies of some specific projects of ours, looking at where there's, through testing, time, dollars, and yes, carbon were all saved. And the key to that, that's not a 2-for-1, that's a 3-for-1 value message. Personally, I spent a lot of time in my career of late on embodied carbon, and this is an exciting topic. And I'm not saying that just to be patronizing to the group here on the phone or in this call. We have an ability to make an outsized influence on reducing carbon on our projects with really some pretty simple actions based on improving our understanding of the variables we're working with and improving our quality control. You know, better quality control and testing is the easy low-hanging fruit for making an outside difference. And yes, that's about dollars, but it's about carbon. And I know I'm speaking to the choir on this front, but let me give you a few data points on what I mean, and I think how we can also start to talk about this. So what do I mean when we talk about embodied carbon? In fact, what does the term even really mean? We're in a time of change. As the global population urbanizes over the next 30 years, there's a projection for about a 30% increase for the level we are building today in our cities. Now, I don't know if that number is right, or if the statistic of 3,600 more buildings per day in urbanized areas by 2050 is the right number. You know, maybe the population won't move into the cities quite that fast, but these are big numbers. And sorry, I'm having a little short time in getting this to move right. But in order to meet this effectively, what I'm going to call an unlimited demand, we have an unlimited amount of resources. Now, according to a 2021 Circular Economy report, 45% of global materials annually extracted from the planet go towards the built environment. So we need to more thoughtfully consider how we use our limited resources. And as creators of the built environment, we're both at the core of our problems and our solutions for how we choose to act on climate change. Now, if you think further about the materials, waste is often 10% of a project budget or more. And that's before we talk about what is or is not being recycled. And certainly foundation systems are one of those places where perhaps waste is one of the greatest amounts that happens during construction. Consider those numbers for a minute and then think about that a contractor's profit margins can often be under 5%. And certainly when we're looking at the end of the life of a project, well in excess of 30% of what gets taken down is often not reused. Frankly, the last presentation is a great example of, you know, how can we do more with what we already have? But when we do take things down, a surprising amount does end up all going to the landfill. So 38% of our built environment, of our total global emissions, if 38% of that is in our built environment, what are we going to do and how do we act on that? And maybe one last bullet point here to think about, the clients that are, at least in the built environment of the buildings that we do, the clients and the tenants moving into these buildings, they're making a lot of ambitious climate pledges. often they really don't know how they're going to achieve these goals, but they're turning to those expending the most carbon in creating their infrastructure needs. And they're turning to us and saying, what can we do to help them towards their goals, to show movement and action towards those? So embodied carbon and progressive action on showing how to reduce it is becoming a differentiator of who's getting the projects. Gerald, I see a hand up.
Sorry about this. Not intentional.
Okay. Remember this, if nothing else, you can't manage what you don't measure. And I think that's really an ultimate part of what we are talking about here. So in the DNA of embodied carbon tracking on a project, it really comes down to three things. It starts with the material quantity estimate. What are the materials going into the building? As a design team, do we know these? Are we tracking them? How well do we report those out? There's a lot of focus these days. And it's not showing. Oh, there we go. What I'll call environmental product declarations that are coming out, basically like a nutrition label that goes with the material. It reports the amount of carbon or the global warming potential in the materials. Concrete, steel industry, these are much more prevalent these days. And ultimately that becomes a total amount of embodied carbon that goes into a building. This is how the design teams are talking about the information. And it comes a lot, especially into our above grade structures. We're not really talking a lot about it on foundations, but this is a conversation that's coming quite a bit more. Now, tools like the embodied carbon and construction calculator, just to give you a flavor of how fast this topic's moving. This is a national database of these environmental product declarations that was launched about 2 years ago to make the information publicly available. So it puts all these EPDs for different materials in one place. In 2 years, we've gone from 800 to over 45,000 EPDs for the concrete industry alone in this national database. It's a very quickly moving topic. It's getting a lot of buzz. And questions are starting to be asked about this double bottom line accounting, cost and carbon. And so just reiterating what I was saying, this I think is coming more to our foundation systems to talk about double bottom line, bringing carbon into the conversation. And I think whole building LCA is how we talk about the whole project, but foundations and excavations are certainly where it's coming up next. And again, this is just giving flavors of the type of evaluations and the graphics that people are using right now to help describe to owners what the carbon footprint is that's going into their buildings, and then helping devise strategies of what we do about it. And this is where testing and just looking through quality control, how we can reduce that carbon footprint, huge home. So carbon reduction opportunities, what can we be doing about that when we're talking about our piles? Now, certainly one is find the 2-for-1s, find the 3-for-1 systems. When we put a system into place, make it do a job more than once. Now, this isn't testing, but if we're putting a lot of piles into the ground, using geothermal piles for heat exchange to where there's a more stable heat source or a cooling source at depth. I think the Google project that was just one of their recent projects just being completed in the Silicon Valley area, every single pile is I think it's the world's largest installation of geothermal piles in the world is just being finished right now. Now, the first thing that goes to my mind, I'm looking at all those empty pipes going up and down this pile. What could we do with that for testing to validate integrity of that pile, actually before we filled it up with a fluid that we're using it for thermal heat exchange? Something to think about maybe for a later conversation. Recycled use of materials, steel pipe piles. This is the T-Mobile Park where the Mariners play in Seattle. That entire project sits on concrete filled steel pipe piles, but all of the steel for those piles came as a contractor bidder alternate design, where it turned out that there was a oil gas line that had been procured fabricated, but didn't actually go into place. So there's a whole bunch of steel, very specialty diameter and wall thickness of steel for this gas line that never went in. We ended up redesigning the foundation of the building to reuse that same material. So instead of scrapping that pipeline, remelting it and putting it someplace else, we went and used those. And in fact, those became the pipe piles for this project. Reusing materials whenever possible. I love the last example on repurposing the bridge versus just starting out new. There's a carbon narrative to tell in that, in addition to just the cost savings, and clients are going to be very receptive to those narratives when we can tell them. Now, when we talk about concrete, without question, it's one of the biggest places there's a carbon sink in what we're doing with the built environment. And it typically comes down to the cement. What can we do with the cement? There's new types of cement coming out, type 1L cement, which it's a limestone blend. It's still a type 1 cement. The ASTM designation for it is C595. It ends up being, sorry, the touchy here on the mouse. It ends up being about a 15 to 20% reduction just if we change to type 1L cement. You know, the other big variables that go into making ready-mix concrete, other cement replacements, fly ash, slag, glass powders starting to be used and talked about more. But I want to talk about for a moment about aggregate. It is the biggest by volume component that goes into making ready-mix concrete. And quality control of the aggregate supply is a huge opportunity to reduce the carbon footprint of the concrete going into any of our elements. And I'll use an example of a project in LA that we recently did, where simply by tightening up quality control of at the batch plant, tightening up the aggregate in the LA market, there's a very poor aggregate supply. It's very inconsistent. And so the way that the ready-mix industry has solved that is they just put more cement in the concrete to make sure they make the strength that we need as the structural engineer. But if we just studying that for a bit, we change the aggregate source to a more consistent imported higher quality, in this case, quartz pea gravel orca aggregate that was being barged down the West Coast. We went from the red bell curve to the blue bell curve. And the end of the day was, even including after shipping the rock down the coast, was a 24% carbon reduction on the project at no cost increase. And the reason it was no cost increase is, yes, it was expensive rock, but rock is cheaper than cement. And for the same volume of ready-mix concrete, the supplier figured out that by using the better quality rock, taking cement out, they could save money and create a lower carbon footprint mix. It still met our design performance characteristics for the strength of concrete we needed. That's the win-win scenarios we want to find. And that's an easy idea that could totally be translatable over to the foundation elements. Key with this, through quality control, through better testing, we can lower our carbon footprint. And so, of course, that moves into not just the material, concrete, and it's the purpose of most of this conversation. We can talk about piles and deep foundation elements. Too often today, what we will do is preliminary design, and then we'll go out and do testing to validate it. And then we immediately move into production with some amount of validation testing for what gets put into place. When we do that, we are doing testing to ensure the integrity of our final design, but we're not really taking advantage of that to optimize the design. What really needs to happen is we need to do more testing earlier, and there needs to be a do loop in the process. We need to do testing, we need to get the values, and there needs to be time that allows us to go in and refine and optimize the design, and then come back with a finalized, more optimal solution based on what we discovered or found out through that initial testing. I know this group would know that, but getting the testing done earlier so that we actually can react to the information we get, it is probably one of the biggest things that is missing often in our foundation elements to truly take advantage of the information that you guys have to offer when we do more testing. Now, ultimately, I advocate this a lot on our projects when we can, is go more to a performance-oriented procurement process where we as designers tell you the information we need and then get out of the way and stop trying to be the experts on things we are not the experts on. So like as an example with foundation elements, especially where there's a number of different proprietary systems and there is, depending on the equipment that someone has, their ability to what they can put into the ground. You know, if I simply put out there the criteria, hey, I need an element at this location with this capacity and this deflection criteria, put that out to the market early enough where we can react to it. And we should be asking back, tell me how much it costs, tell me how fast you can put it in, and tell me the carbon footprint that goes with your system that would go into place. Do that type of double and triple bottom line evaluation as a performance process, and then bring the design build contractor into part of the team as we complete the design. That's usually where we get the best and the highest, both the highest performing, but also the lowest carbon footprint and cost solutions. So let me walk you through a couple of case study projects of buildings that we have recently done to tell some of these stories of exactly what we've just been talking about. So this project here, it's a 34-story apartment tower in Milwaukee called 777. It has 16-inch diameter concrete-filled pipe piles. We did both static and dynamic testing during the design phase to change the factor of safety on the piles from 3 down to a factor of 2. Now, the decision for the testing happened in schematics. The actual testing happened near the end of design development. We had results in hand early in the construction document phase, which gave us time to then adjust and iterate the final design before we finalized the project. Now, the test piles were retested about a month after they were put in to allow for both geotechnical capacity set up and for the concrete in them to reach strength. The upfront testing in terms of just pure concrete rebar and steel savings ended up being about $2 million and 6 weeks off the schedule as confirmed by our geotechnical engineer. Adding another layer to that conversation, that was about 1.5 million kilograms of carbon saved, or the equivalent of 340 cars taken off the road for a year just by doing that early testing. That's dollars, time, and carbon reduced through testing that happened during the design process and then taken advantage of before we finalize design. That's a win, win, and a win, all three together. Now, next project here, this one is actually underway right now. This is a 35-story, million square foot office tower in downtown Cleveland. Project name is under an NDA at the moment, but if you're from Cleveland, you'll probably know which building I'm talking about. Drilled shafts are up to 8.5 foot diameter, and they're up to 200 feet long under the core of this building. Couple things. We did a method shaft. The sacrificial method shaft was drilled to confirm the large excavation for those shafts could be completed without the need for permanent casing. Now, in the method shaft, the shaft excavation was monitored for both plumbness and consistency through of cross-section through thermal integrity profile testing and sonic logging of the excavation under the slurry to help validate that plumbness and consistency of the cross-section. And then after the method shaft is done, we also cored it, or we'll be coring it and testing that for the concrete. Once confirmed, we look to be saving 5 million pounds of steel by eliminating the permanent casing through validating, proving that we can do, that the team will be able to do what they say they're going to do. That's about 4 million kilograms of carbon saved. That's equivalent of 900 cars being taken off the road for a full year by doing this additional testing. And that method shaft is actually happening right now as we speak. And so moving to a couple of projects that we've done in Chicago, this is our 150 North Riverside, 52 stories, 1.3 million square feet. It's right on the Chicago River. The project's very aggressive design where it's only the core that is touching to the ground of that whole office tower. Would not have been possible without substantial exploration and of the site and knowing where the bedrock is, knowing exactly the capacity of what we had in the foundations before we founded the tower on it. So we had advanced cores into rock for each of the 18 rock socketed caissons. And we did that to confirm at each caisson rock quality and capacity. Here we took the caissons up to a 400 KSF bearing capacity of each shaft. This occurred before the design was finalized, giving us the opportunity to tune the final design, including shaft lengths within their final capacities. And the project also had a substantial podium of H-piles and micropiles. Those low test elements were up to 300 tons. Total, we saved about 1 million pounds of steel in the piles and the H-piles just through the testing that we were doing. Sorry, my image went too far there. That was about 800 kilograms of carbon reduced on just the H-piles and the micropiles only. So, you know, again, a win-win scenario of dollars and carbon. And then lastly, I want to talk about our Vista Tower in Chicago. This is 1,200 feet tall. It's the world's tallest building designed by a woman. It's Jeannie Gang of Studio Gang Architects. And just talking a little bit about the foundations there, it's founded on rock socketed caissons. The bearing capacity of these through Osterberg load cell testing, went up to 500 KSF. And we actually couldn't go higher than that because uplift forces on the tower started to control more than compression. But after method shaft validation, total project savings of materials, especially by being able to also minimize the amount of permanent casings, was about $1.3 million and about 1 million kilograms of CO2 that was saved. So just finalizing what we're talking about, testing saves dollars, it saves carbon, and it helps reduce risk. And I think this is a win-win scenario that the more you can bring this into your narrative of how you explain what you're doing to people, I think it's just another variable for a win-win-win conversation that should always come out. And at that, let me stop and take any questions you guys might have.
Don, thank you very much for that presentation. As a member of the Testing Evaluation Committee, obviously the fact you promote testing is near and dear to my heart. As chair of the Sustainability Committee, I'm obviously even more excited about what you just what you just mentioned in here, saving carbon as well. And then when you put everything together, I think it is indeed more than just a win-win situation.